Imagine you wake up tomorrow and the moon is gone, not destroyed, just missing. The sky is empty. The tides have stopped. The ocean's eerily still, less like bathwater no one is stirring. Nights are darker than you've ever seen them. The stars are brighter. The sky feels bigger and colder. Within weeks, the weather goes wrong. Storms grow stronger than they should be. The jet stream wanders. Coral reefs die because the lunar spawning signal is gone. Sea turtles can't find their beaches. Migratory birds lose their way. Within years, Earth's axial tilt begins to wobble. Not catastrophically, not yet. But over geological time, the wobble becomes a slow tumble. Earth's poles drift. The equator shifts. Continents end up at latitudes they were never meant to occupy. Ice caps form where there used to be jungle. The planet, without its anchor, slowly forgets which way is up. This is the version of Earth we should have had. The version that, by every reasonable model of how planets form, we should be living on right now. Because the truth is, Earth's moon shouldn't exist. The fact that there is a giant gray rock hanging in the sky above your head, exactly the right size, at exactly the right distance, doing exactly the right job to keep this planet livable, is one of the most improbable accidents in the history of the solar system. And the further you look into it, the stranger it gets. This is the story of how our moon is unique, not just different, not just unusual, unique in ways that, when you stack them up next to each other, start to feel almost suspicious. Let's start with the most basic question. What is a moon, actually? The technical definition is boring. A moon is any natural object that orbits a planet rather than orbiting the sun directly. By that definition, our solar system has around 290 known moons, and we keep finding more. Saturn has at least 146. Jupiter has 95. Even tiny Mars has 2. But here's where it gets interesting. Almost every moon in the solar system falls into one of 2 categories. The first category is captured moons, objects, usually asteroids, that wandered too close to a planet's gravity and got snagged. Most of Jupiter's smaller moons are captured. Mars's Phobos and Deimos are almost certainly captured asteroids. You can tell because they look like asteroids. Irregular, lumpy, chemically alien to the planet they orbit. The second category is accreted moons, moons that formed alongside their planet, condensing out of the same disk of gas and dust that built the planet itself. Io, Europa, Ganymede, Titan, they all formed this way. Miniature solar systems in their own right. Our moon fits neither category. It's not captured. Too large. Too chemically similar to Earth. Too stable in its orbit. It's not accreted. If it had formed alongside Earth from the same primordial disk, it would have a similar iron-rich core. It doesn't. Our moon has a tiny iron core, disproportionately small, while Earth has an enormous one. 2 objects that formed in the same place at the same time should not have such different interiors. So where did the moon come from? For about 100 years, scientists threw out hypotheses and watched them get knocked down. Maybe the moon was flung out of the Pacific when Earth was young. Maybe Earth and the moon were a binary planet from the start. Maybe the moon was captured by some unlikely gravitational fluke. None of these survived the Apollo samples. When astronauts brought back lunar rocks between 1969 and 1972, the chemistry told a single, unambiguous story. The moon's isotopic ratios, oxygen, titanium, tungsten, chromium, matched Earth's mantle so precisely that the 2 bodies must have shared the same source material. But the moon was also bone dry, almost completely lacking in volatile elements like water and potassium, which would have been baked out by enormous heat. The only theory that explained all of this was almost too dramatic to be believed. About 4.5 billion years ago, when Earth was still a young, molten world only 30 million years old, something the size of Mars crashed into it. We've given that something a name: Theia. The collision wasn't a glancing blow. It was a near-direct impact at about 9,000 miles per hour. Theia was effectively destroyed. Earth was nearly destroyed. A ring of vaporized rock and metal was flung into space, and within somewhere between a few hours and a few hundred years, that ring coalesced into the moon. Our moon was born from the corpse of a vanished planet, hammered out of the side of a wounded Earth. That alone would make it unusual, but it's only the beginning. Because there's something the textbooks don't tell you about this story. The giant impact hypothesis isn't actually settled. There are serious problems with it that planetary scientists have been arguing about for decades, and competing models, the synestia hypothesis, the multiple impact model, even an idea involving a natural nuclear reactor inside the early Earth, are still on the table. The moon's origin is the most taught piece of settled science in planetary geology that isn't actually settled. And the deepest problem with it is chemical. Here is a story most science viewers have never heard. In the early 1970s, a young geochemist named Robin Brett got his first look at the isotopic data from Apollo samples. He expected to see something specific: a fingerprint. Every body in the solar system has its own isotopic signature, a kind of chemical accent that tells you where in the early solar nebula it formed. Mars rocks have a Martian accent. Meteorites from the asteroid belt have an asteroid belt accent. Earth has its own. Brett expected the moon to have a mixed accent, part Earth, part Theia, because if the giant impact hypothesis was right, the moon was built from debris of both bodies, and Theia had presumably formed somewhere else in the solar system with a different isotopic signature. The data came back. The moon's oxygen isotopes matched Earth's. Exactly, within the limits of the instruments. Brett and everyone else looking at the data assumed it was a measurement error. Better instruments would surely find Theia's signature. Better instruments came. They found nothing. The match held for oxygen, then for titanium, then for tungsten, then for chromium, then for silicon. Every isotope ratio anyone checked came back the same. The moon was, chemically, a piece of Earth's mantle. Theia had vanished. This is called the isotopic crisis, and it has been quietly destabilizing the giant impact hypothesis for 50 years. 3 solutions have been proposed. The first: the impact was so violent and so hot that Earth and Theia completely vaporized into a single mixed cloud before the moon condensed. In 2022, a team at Durham University ran the highest resolution simulation of the impact ever attempted and proposed that the moon may have formed almost immediately, within hours, from a fully vaporized disk, rather than over centuries from a debris ring. In this scenario, the chemistry homogenizes naturally. The second, Theia happened to have nearly the same composition as Earth because it formed at the same distance from the Sun. Statistically unlikely, but possible. The third, and this is the strangest one, is that pieces of Theia may still be inside Earth. In 2023, researchers at Caltech proposed that 2 massive, unexplained blobs of dense material near Earth's core mantle boundary, which seismologists have known about for decades, may actually be the buried remains of Theia. If true, our planet didn't just absorb Theia, It still carries her 4.5 billion years later in its deepest layers. Whatever the explanation, the point stands. The moon is chemically a piece of Earth. It is, in a very literal sense, our planet's child. And there is no other moon-planet pair in the solar system that has this kind of chemical relationship. Only Earth and its moon share a body. Look up at the moon tonight. It looks pretty big, right? Bigger than the stars. Bigger than any planet. Big enough to fill its corner of the sky. You're not imagining that. The moon is genuinely absurdly large. Earth's moon is 2,159 miles across, roughly a quarter of Earth's diameter. By mass, about 1.2% of Earth. Those numbers don't sound dramatic until you compare them to every other moon-planet pair in the solar system. Phobos is about 0.0000016% the mass of Mars. Triton is about 0.02% the mass of Neptune. Ganymede, the largest moon in the solar system, larger than the planet Mercury, is still only 0.008% of Jupiter's mass. Titan, second largest, is 0.024% of Saturn. Our moon is 1.2% of Earth's mass. That's 50 times the ratio of Ganymede to Jupiter, hundreds of times the ratio of any inner planet's moon to its host. By every reasonable measure, Earth's moon is the largest moon-to-planet ratio of any major planet in the solar system. The only object that beats it is Charon, the moon of the dwarf planet Pluto. And Charon is so massive relative to Pluto that astronomers don't even call it a moon. They call the Pluto-Charon system a double dwarf planet. By the standards we use for everything else in the solar system, Earth and the moon are barely a planet and its satellite. We are almost a double planet. And this matters for reasons that go well beyond aesthetics. A moon this large exerts gravitational effects that smaller moons simply cannot. It can stabilize a planet's axial tilt. It can drive tides large enough to reshape coastlines and drive the chemistry of life. It can carve out an orbital relationship so intimate that the two bodies become tidally locked, with one face of the moon turned permanently toward the planet, which is exactly what has happened with us. The probability of a planet like Earth ending up with a moon like ours is, by the best models we have, somewhere around 1 in 10. Maybe less. Most rocky planets in the universe, and there are billions of them, should have either small captured moons, like Mars's, or no moons at all. And here's where it gets even stranger. Over the past 3 decades, astronomers have discovered more than 5,500 exoplanets, worlds orbiting other stars. We have searched with great care for exomoons, moons orbiting those worlds. We found exactly 2 candidates, both of them disputed, both of them enormous, gas giants orbiting other gas giants. We have not found a single confirmed Earth-Moon analog anywhere in the galaxy. That might just be a detection problem. Finding a small rocky moon around a small rocky planet is at the absolute edge of what current telescopes can do. But it's worth saying clearly, every search we've done so far has failed to find another Earth-Moon system. We may be alone, or we may just be early. We don't know yet. What we do know is that in our own backyard, Earth's moon is the outlier, the freak, the one that doesn't fit, and the size isn't even the strangest part. Let me tell you something about the moon that almost nobody knows, even though it's been true for as long as humans have existed. The moon is leaving, not dramatically, not visibly, but measurably, continuously, and irreversibly. The moon is receding from Earth at a rate of about 3.8 centimeters per year. That's roughly the speed at which your fingernails grow. We know this with extraordinary precision because of an experiment that began in 1969. When Apollo 11 landed on the Sea of Tranquility, Buzz Aldrin set up a small device on the lunar surface, a retroreflector. It's basically a sophisticated array of mirrors designed to bounce laser light directly back to wherever it came from. Apollos 14 and 15 left similar reflectors. The Soviet lunar missions left 2 more. For over 50 years, observatories on Earth have been firing precisely timed laser pulses at those reflectors and measuring how long the light takes to come back. The technique is called lunar laser ranging, and it can measure the distance to the moon to within a few millimeters. The data is unambiguous. The moon is getting farther away every year. The reason is tides, but not in the way you might expect. When the moon's gravity pulls on Earth's oceans, it creates the familiar tidal bulges. But Earth is rotating faster than the moon is orbiting, so the planet's rotation drags those bulges slightly ahead of the moon's position. The bulge's gravity then tugs the moon forward in its orbit. That extra forward energy boosts the moon into a higher orbit, and a higher orbit means a longer distance. The energy has to come from somewhere. It comes from Earth's rotation, which means as the moon recedes, Earth's day is slowly getting longer. About 1.8 milliseconds per century. Imperceptible over a human lifetime. Catastrophic over geological time. Run the math backward and you get something astonishing. When the moon first formed, it was somewhere between 14,000 and 22,000 miles from Earth's surface. For reference, the moon today is about 239,000 miles away. So it was, when it formed, somewhere around 10 to 15 times closer than it is now. Imagine that sky. The young moon would have filled an enormous portion of it, not the small, manageable disk we see tonight. Something the size of a beach ball held at arm's length, maybe larger, and it would have been hot, still cooling from its formation, possibly glowing red. The young Earth looking up would have seen a vast, red, churning companion looming overhead, close enough to feel like it might fall. The tides would have been monstrous. With the moon so close, tidal bulges may have been hundreds or thousands of feet tall. Entire oceans would have surged across the planet's surface every few hours because Earth was also rotating much faster. A day on early Earth lasted about 6 hours, not 24. There's a recent twist to this story worth mentioning. In December 2024, a team publishing in Nature presented new evidence suggesting the moon may be about 100 million years older than we previously thought, closer to 1 billion years rather than 4.4 billion. The implication is that the moon went through a period of intense tidal heating shortly after its formation that reset many of its surface rocks, which is what previous dating methods were actually measuring. The moon is older than its own surface suggests. That older moon, that hotter early relationship between Earth and its companion, these are corrections we're still working out. The story is more recent and more unsettled than the textbooks suggest, but the broad picture is clear. Over 4.5 billion years, the moon slowly receded. The tides shrank. Earth's spin slowed. The day stretched out. The sky got quieter. We are right now living in a brief and unrepeatable window. The moon has retreated to the exact distance where it stabilizes our climate without overwhelming our oceans, where it's small enough in the sky to be beautiful but still large enough to matter. In another 600 million years, the moon will have receded far enough that total solar eclipses will no longer be possible. The moon will appear too small in the sky to fully cover the sun, the cosmic coincidence that has been used by humans for thousands of years to mark sacred moments, and that allowed Eddington to verify Einstein's general relativity in 1919. will end. We are alive during the eclipse era. It won't last. I mentioned earlier that without the moon, Earth's axial tilt would become unstable. I want to come back to that because it may be the single most important thing the moon does for us, and the science behind the claim is more contested than you might think. Earth's axis is tilted by about 23.5 degrees relative to its orbit around the Sun. That tilt is the reason we have seasons. It has wobbled only a few degrees in either direction over millions of years, in a slow rhythm called precession. That stability is unusual. Compare it to Mars. Mars has two tiny moons, Phobos and Deimos, neither large enough to exert any meaningful gravitational stabilization. As a result, Mars's axial tilt is chaotic. Over the past several million years, it has swung between roughly 10 degrees and 60 degrees. When Mars's axis is steep, its poles tip toward the Sun. The polar ice caps sublimate into the atmosphere, and the planet's climate dramatically reorganizes itself. Mars is a planet that climatically can't sit still. Earth, by comparison, is a metronome. In 1993, the French astronomer Jacques Lascar published a landmark simulation suggesting that without the moon, Earth's axial tilt could swing chaotically between 0 and 85 degrees over geological time. The implication was stark. No moon, no stable climate. And no stable climate meant, almost certainly, no complex life. That paper became one of the foundational citations for what's called the rare Earth hypothesis, the idea that the specific conditions allowing complex life may be vanishingly rare in the universe. Here's what most documentaries leave out. Laskar's result has been challenged. In 2011, a researcher named Jason Barnes, working with collaborators including Lascar himself, ran updated simulations and found that the situation is more complicated than the 1993 paper suggested. A moonless Earth wouldn't necessarily tumble chaotically. If the planet were rotating quickly, say with a day length of about 10 hours instead of 24, the axial tilt would actually be quite stable, varying by only about 10 degrees over hundreds of millions of years. The moon, in slowing Earth's rotation through tidal friction, may have actually created the instability problem it then solves. In other words, without the moon, Earth might still have had a stable axis, just for different reasons. Or it might not have. The honest answer is that we don't fully know. But here's the part that hasn't been overturned. With the rotation rate Earth actually has, a 24-hour day, the moon is essential for axial stability. The geometry locks. Remove the moon from the Earth we actually live on, and the axis does become chaotic on timescales of a few 100 million years. So the moon's role isn't quite the simple "without it, we'd be Mars" story you've heard. It's a more entangled story, where the moon both shaped our rotation rate and then stabilized the world that rotation rate produced. Either way, the result is what matters. Our axial tilt has stayed within about 1.3 degrees of its current value for as long as we can measure. That stability is why agriculture works. It's why ice ages come and go in predictable Milankovitch cycles instead of erratic catastrophes. It's why human civilization, which only emerged in the past 10,000 years, has had a stable enough climate to develop at all. If a large moon is what it takes to lock a planet into long-term climatic stability, then the search for life elsewhere in the universe may need to be narrower than we've been told. We shouldn't just be looking for Earth-sized planets in the habitable zone. We should be looking for Earth-sized planets with large moons in the habitable zone. And we don't yet know how rare that combination is. It may be that we are not just one of many Earths in the galaxy. We may be one of very few stabilized worlds capable of hosting beings who can ask questions about themselves. If the moon's role in stabilizing our axis is the quiet, invisible gift, then the tides are the loud one. Twice a day, every coast on Earth experiences the rising and falling of the sea. We've gotten so used to this that we forget how strange it is that a rock 239,000 miles away can reach down through space and pull entire oceans up and down on a planetary scale, on a clock so reliable you can set your calendar by it. The tides are mostly the moon's doing. The sun contributes too, about 46% as much pull as the moon. But the moon, because it's so much closer, dominates the rhythm. When the sun and moon align during new and full moons, the tides amplify into the larger spring tides. When they pull at right angles during quarter moons, we get the gentler neap tides. That rhythm has been going on for 4.5 billion years, and it may be the reason you exist. The leading theory of how life emerged on Earth involves the chemistry of warm, mineral-rich water concentrated through repeated cycles of wetting and drying. Tidal pools, the small basins of seawater left behind on rocky coasts as the tide retreats, are nature's perfect chemistry laboratory. Twice a day, they fill with fresh seawater, swirl with dissolved minerals and organic molecules, and then partially evaporate as the tide goes out, concentrating those molecules into ever thicker soups. Then the next tide comes in and resets the experiment. Over millions of years, those cycles may have been the engine that drove the random assembly of the first self-replicating molecules. The RNA world hypothesis, currently the leading model for the origin of life, requires exactly this kind of concentration and dilution cycling to plausibly produce the first replicators. Tidal pools, and specifically the enormous tidal pools generated by the early close moon, may have been the only environment on early Earth where the chemistry worked. This isn't proven. It may never be proven. The rocks from that era are mostly destroyed, and the chemistry has long since washed away. But the tidal pool hypothesis is one of the leading models, and it requires tides, significant ones, reliable ones, Earth and moon-sized ones. A moonless Earth would still have tides because the sun would still tug on the oceans. But those tides would be less than half as strong, less variable, and far less productive as a chemical engine. Life might still have emerged, or it might not have. We have a sample size of one, a single planet, and that planet had a large moon. We can't disentangle the variables. What we can say is this: every coral reef, every mangrove forest, every Grunion run, every fiddler crab, every species that times its reproduction or feeding or migration to the rhythm of the tides, and there are thousands, owes its existence to the moon. The biosphere is, in subtle and pervasive ways, lunar. We have shaped ourselves around its pull. Coral spawning across enormous reef systems is precisely synchronized to lunar light. Entire reefs release eggs and sperm into the water on the same night, year after year, triggered by the moon. Sea turtles navigate by it. Dung beetles roll their dung balls in straight lines using the Milky Way as a guide, but they also adjust their paths based on lunar position. Lions hunt more aggressively during dark moons. Plankton rise and fall in the water column in lunar rhythms. The moon is not just a light in the sky, it is a metronome that the entire biosphere has been beating against for billions of years. I want to come back to something I mentioned earlier because it's the single strangest fact about the moon, and most people have never stopped to consider how strange it actually is. The moon and the sun appear to be exactly the same size in our sky. This is why total solar eclipses are possible. The moon, when it passes between us and the sun, fits over the sun's disk with breathtaking precision, covering it almost exactly, leaving only the corona visible as a thin halo of light. If the moon were slightly smaller, eclipses would always be annular. A ring of sunlight would remain visible. If the moon were slightly larger, the sun would be totally obscured and we'd never see the corona at all. We are positioned by coincidence in the narrow band where the geometry works out perfectly. The sun is about 400 times wider than the moon. The sun is also, on average, about 400 times farther from Earth than the moon is. Those two numbers, 400 and 400, are what make the disks appear the same size. There is no physical law that requires this. No principle of gravity or orbital mechanics demands it. It is, as far as we can tell, pure cosmic coincidence. The moon happens to be the right size and at the right distance, at this specific point in Earth's history, to perfectly match the sun. This coincidence has had enormous consequences for science. It was during a total solar eclipse on May 29, 1919, that Arthur Eddington led an expedition to the island of Principe to measure the deflection of starlight by the sun's gravity. Stars visible near the eclipsed sun appeared shifted from their normal positions by exactly the amount Einstein's theory of general relativity predicted. The result made Einstein world famous overnight, and it remains one of the most important experimental confirmations in the history of physics. We could not have tested general relativity in 1919 without our moon being exactly the size and distance it is. And as I mentioned earlier, this won't last. The moon is receding from Earth at 3.8 centimeters per year. As it gets farther away, it appears smaller in the sky. At some point, current estimates put it at around 600 million years from now, the moon will appear too small to fully cover the sun. Total solar eclipses will end. Only annular eclipses will remain. We are alive in the eclipse window. Humans have existed for about 300,000 years. The eclipse window has existed for maybe 1 billion years on the early end, with 600 million more years to go. In the geological lifetime of our planet, that window is a brief, glittering chapter, and we happen to be reading it. There is something almost unbearable about that when you sit with it. The universe is not designed for us. It is not arranged for our benefit. And yet, by what appears to be pure accident, we find ourselves on a planet where the largest moon-to-planet ratio in the solar system happens to orbit at exactly the distance where it perfectly eclipses the star we orbit, during exactly the era when a species has evolved that is capable of noticing. Other intelligent species, if they existed on Earth 1 billion years ago, or will exist 1 billion years from now, would not see what we see. The eclipses we witness are ours alone. So what does all of this add up to? In 2000, the paleontologist Peter Ward and the astronomer Donald Brownlee published a book called Rare Earth that argued something deeply unfashionable in astrobiology at the time. Complex life may be extraordinarily uncommon in the universe, even if microbial life is everywhere. Their argument rested on a long list of conditions that a planet needs to meet: the right star, the right distance, the right plate tectonics, the right atmosphere, the right galactic neighborhood. And near the top of that list was a large moon. A quarter century later, the rare Earth hypothesis is no longer fringe. It's one of several leading frameworks for thinking about the Fermi paradox. The question of why, in a universe of 2 trillion galaxies, we don't see any evidence of other civilizations. There are many possible answers. Maybe civilizations destroy themselves. Maybe they hide. Maybe interstellar travel is harder than we think. But one answer increasingly hard to dismiss, is that the chain of accidents required to produce a stable, complex, technology-using species is so long and so improbable that we may genuinely be alone in our corner of the galaxy, maybe in the entire galaxy. And the moon sits near the center of that chain. Consider what had to happen. A planet the size of Mars had to collide with the early Earth at exactly the right angle and exactly the right speed. Not so fast that both bodies were destroyed, not so slow that the impactor merely merged with Earth without producing a debris ring. The resulting moon had to form at exactly the right mass, large enough to stabilize Earth's eventual axial tilt, but not so large that it dominated the planet's geology. The moon had to reseed at exactly the right rate, slowly enough that productive tides have persisted for billions of years, but quickly enough that we're not still living under a glowing red sky. The moon had to end up at exactly the right distance, during exactly the right era, to produce eclipses just as a species emerged that was capable of noticing them and using them to verify the structure of spacetime. Every one of these things had to happen. Change any of them, make Thea a little larger, or the impact a little faster, or the resulting moon a little smaller, or the receding rate a little different, and you erase the Earth we know. You erase the seasons. You erase the tides. You erase the eclipses. Maybe you erase us. There are two honest ways to interpret this. The first is the anthropic interpretation. We notice these coincidences because we are here to notice them. On the trillions of other planets where the configuration didn't work, no one is writing scripts about how strange it all is. The coincidences feel meaningful because we are the survivors of a cosmic lottery. The universe is full of dead worlds. We happen to be alive on the rare one that worked. The second is more uncomfortable. If complex life truly does require a configuration this specific, then we may be much rarer than we like to think. Earth may not be one of many. Earth may be one of very few. And the moon, that quiet gray disk that has hung in our sky for as long as our species has existed, may be the most visible evidence we have that something extraordinary happened here. We don't yet know which interpretation is right. The James Webb Space Telescope is searching exoplanet atmospheres for biosignatures. Future missions will look for exomoons. Within a few decades, we may have a much better answer to the question of whether Earth-Moon systems are common or vanishingly rare. Until then, the moon is the clue we have, and it points, however softly, toward the second answer. Tonight, when it gets dark, go outside and look up. If the moon is visible, and most nights it is, take a moment to really see it. Notice the dark patches that we now know are ancient lava plains, frozen in place since the early solar system. Notice the bright highlands, scarred by 4 billion years of impacts. Notice how big it looks. Notice how close it feels. And then think about everything that had to happen for that view to exist. A planet the size of Mars, traveling on a collision course 4.5 billion years ago, struck a young Earth at exactly the right angle and exactly the right speed to fling debris into orbit without destroying both worlds entirely. That debris coalesced into a moon massive enough to stabilize Earth's axis, but small enough not to dominate it. The moon drifted outward at exactly the rate needed to allow tides to remain productive for billions of years. It happened to settle into the narrow distance range where its apparent size matches the sun's, during exactly the era when a species capable of noticing eclipses evolved on the planet below. We exist in the narrow band where it all worked. We are alive during the brief window where the geometry is perfect. We are looking up at a sky that, on the scale of cosmic time, won't look like this for very much longer. The moon is leaving, slowly, patiently, irreversibly, 3.8 centimeters every year. In 600 million years, the eclipses will be gone. In a few billion years, the moon will be so distant that its stabilizing grip on our axis will weaken, and Earth, if it still exists in any recognizable form, will begin to wobble. But not yet. Not tonight. Tonight, the moon is still there, still the right size, still the right distance, still doing the quiet, ancient work of holding our planet steady, lifting our oceans, and reminding us, every time we look up, that we are the product of an accident so improbable that it borders on the miraculous. We are alive in the eclipse era. We are the witnesses to a coincidence that won't last. So look up while you can.